Welcome to another episode of CS 340 with your hosts, Frank Wood and Payman Golami, excuse me. Oh dear. So today we're gonna sort of move towards non-parametric models. Remember the course webpage, the second assignment, like all assignments, are released so that you can do them at your leisure, but the second assignment is out, it's long, start early. Make sure that you follow the submission instructions, lest we have to give you bad marks for the homework. So last time we talked about email spam filtering. I don't know if you remember or not, but basically the idea is we wanted to cast email spam filtering as a supervised learning problem, and we wanted to build a system that filters spam emails based on some sort of features extracted from emails and human given labels of what is spam and not. And we assign, 1 if an email is spam and y equals 0 if it's not spam, and blah, 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 blah. The features for every email basically are binary in the setting of this problem that we considered, basically indicating the presence or absence of a word or phrase, bigram, trigram in the particular document. And the way we looked at it was to look at solving it was to use what we called the naive Bayes classifier, where we use Bayes' rule to construct the conditional probability of interest. This happened last time as well. Where we use Bayes' rule to construct the conditional probability of interest, the probability of an email being spam or not spam conditioned on its features. We construct this via Bayes' rule and estimates of a bunch of conditional probabilities, the marginal probability of an email being spam or not spam, and then the conditional probability of generating a particular feature vector given that an email is spam or not spam. In order to make this tractable, we said that estimating these conditional and marginal probabilities is hard because of the dimension of the space effectively. So we introduced a conditional or used a conditional independence assumption, factorizing the joint over all features into the product of all of the individual conditional probabilities for each of the features conditioned on spam or not spam. And we said that the structure of the program that we're going to induce or train or fit or whatever involves a decision based on estimating these conditional probabilities. And we would return spam if our conditional probability estimate consisting of these guys up here or estimated by the product of these guys in the numerator of Bayes' rule was larger than not spam. In order to compute this, we didn't actually need the evidence or this marginal probability of the feature vector because under Bayes' rule and whatever, we can get rid of it. Just to clarify what's going on again, so naive Bayes formally uses Bayes' rule to construct this or to compute this conditional probability. So we first use Bayes' rule, then we recognize it in the decision rule. The denominator doesn't matter, it's the same for all yi values. And then we make this conditional independence assumption where we break up the joint distribution of the conditional feature distribution given the label into its dimension constituent products, okay? You can look at later on to see how to train or test such a model based on a simple example. But just to, we already talked about how to estimate each of these marginal probabilities, and we talked about a little bit about how to estimate these by basically doing counting in documents. I guess at this point, before you go off and work out an example on your own, at this point, the thing that you should just remember is that when we're training one of these naive Bayes classifiers, the main thing that we're doing is counting to estimate these individual conditional probabilities and counting to estimate this marginal probability. So training means running through the data and counting so that you can estimate all of these probabilities, okay? And in general, we talked about maximum likelihood probability last time, but it's worth thinking about something. Payman, I'm going to have you stand in for the class here, right? Put your thinking cap on, right? Am I cutting out slightly? Is this? Is my audio okay for you, or no?
Yeah, it's good. No, it's normal.
Okay, so I think it must be a problem with Richard's internet. Sorry if that's the case. So here's a question, Payman. Let's say that one of these features right here, we're in 340. Okay, one of these features is payment, presence or absence of payment, right? And we're building spam filters for the class, right? So if it is the case that nobody ever sees an email or labels an email spam with the word payment in it, then what are the knock-on consequences of that? Alan on the chat channel has a good example. So yes, the numerator is 0. That's right. So the numerator in the estimate for the conditional probability of payment given that spam is true would be 0, which means that the probability of any the probability of payment given a spam message of payment appearing in a spam message is 0, right? And Siddharth's got it, right? Any spam message containing payment will never be classified as spam. It has to be classified as not spam, which means that we have an amazing way of breaking all the student spam filters, which is all we have to do is put the word payment in there. So this is a bad classifier, yes, but so thanks, Shanak. But the question is, okay, all right. How about I just not lecture and everybody in the chat channel can just just do it. That's great, right? So why? Okay, so why is it a bad classifier? It's a bad classifier because our estimates of these conditional probabilities are not great. Fine. So that means that we have to figure out some sort of way to make the conditional probability estimates slightly better. And without going into any sort of theoretical explanation or actually much motivation for why we do this, except to say that it makes these estimates better, is that if we want to estimate here now, we were using payment here before, but now we're going to think lactase, right? So that's fine. So our estimate of the conditional probability of lactase, the word appearing, given that it's a spam message, is just the number of spam messages with lactase divided by the total number of spam messages. But there's a problem, which we just identified. If you don't have any spam messages with lactase, then you estimate this probability to be 0. So spam messages with lactase automatically get through because that's the only thing that can happen, right? So a common fix is to basically smooth these probability estimates, right? And the way one way to do this is to add a small number up here and some other small number down here. 1 to the numerator, 2 to the denominator for binary features. And what this acts like is 2 different documents. Like basically, it's like having 2 pseudo documents, if you think about it, where one of them has the word lactase in it and one of them does not have the word lactase in it. Okay, and you can think about augmenting your entire training data set for your spam filter with 2 pseudo documents for every one of these conditional probability estimates, and that smooths this probability estimate in such a way that there are no zeros anywhere, basically. Okay, cool. So typically you do this for all features, and it helps against overfitting by biasing towards a uniform distribution. That's sort of not obvious, actually, except, yeah, it's if there are 0 messages with a particular word and there are 0 spam messages, then then clearly it's half-half.
Wouldn't this affect the smaller data sets? Like this disproportionately affect smaller data sets?
Oh, Leo, good question. Yes, indeed. Obviously, these counts are magic in the sense that they're just counts. So yes, indeed, it will have more smoothing for smaller data sets. But you can argue, and there's lots of ways to do this, but you can argue that when you have smaller data sets, your estimate of that conditional probability would be more noisy anyway. So you probably want to lean towards uniformity anyway, even more, right? This only, so Akeem says this only works for large data sets. Nope, this works for all size data sets. Why is 2 the magic number for binary features? It's a little bit, it depends on, so here's a different case, here's a different case. So, if you use beta, then you should use beta times k, where k is the number of possible values that sums to 1. Where this comes from, or something like this comes from, is a little bit, it's beyond where we are in the course. We won't talk about it too much, right? So let's say that the probability that, what are we after here? Lactase equals 1 given spam. So let's just use this. Let's just call this pi. Okay, that means there's a distribution which is pi and 1 minus pi. So we'll call this pi bar for a vector. Okay, so we can write down a model of, so this map, this Laplace smoothing basically comes from a map estimate where you actually do something like this. Pi bar is drawn beta, and all of the observations from this, I guess we can do binomial, pi n. So the number of 1s, for instance, would be drawn from this distribution. This, if you actually do map estimation and you do Bayes' rule and solve for the analytic posterior and then maximize this thing, this will give you something like Laplace smoothing. It will give you smooth probability estimates for the values of this distribution, right? So, and to be clear, I shouldn't have done this. I should just make that pi, because beta doesn't do it. It's just one-dimensional. So that's probably not clear to most of you, but for those of you who it is, that's okay. If it's not clear, Laplace smoothing, magic numbers on top and bottom, and we'll get to map estimation later and maybe talk a little bit about this beta binomial kind of model. And for those of you who know what beta distributions are and binomial distributions are and know how to do Bayes' rule and do maximum a posteriori already, that's close to where this comes from. Okay, cool. So there's some question, right? So now we know how to maybe make the classifier a little bit better by smoothing probability estimates so that, zero counts don't screw us up so badly, right? But then there's the question of, do we really care equally about what we would call false negatives or false positives, right? So simultaneously, we're going to talk about two different things. One is decision theory, and the other one is some terminology. And the terminology I expect you're familiar with, right? So here, this is the true label, right? So this is unknown to us in general, but for some test data, we'll have labels, right? Over here is what our model predicts, spam or not spam, right? And we already hinted at this with respect to spam filtering, right? Predicting spam when it's actually spam, that's okay, no problem, right? If you predict spam when it's truly not spam, that's really bad, right? That's like you miss a message from your mother, or you miss an important update on 340 or something like that, or you miss a scholarship opportunity. If you predict not spam when it is spam, that's annoying, but it's not the end of the world, right? And obviously, if you predict not spam and it's not spam, that's good, right? So we don't really do a whole lot. I think this is basically all the decision theory we do in the course, because it's not actually really that complicated at the end of the day. But it's worth knowing about this, because when you care about these things in different amounts, then actually the output from your classifier, they'll label the program that you write to classify email, won't just construct the probability estimates, but will emit a label in accordance to the costs that you assign to these different outcomes, taking those into account, right? So I've just said this, the cost of mistakes might be different, right? Letting a spam message through is not such a big deal, but filtering a not spam message, like assigning spam to a not spam message, will make users mad, potentially screw things up badly. So what a decision theoretic framework says to do is to actually assign a cost, sometimes a utility, sometimes a profit, sometimes whatever, but we're going to use units of cost here, to every scenario, so that we say that if we get it right, there's no cost. There's no cost to us at all. But if we predict spam when we should have predicted not spam, that's a false positive, right? And that's very costly, right? It costs 100. We're really, really annoyed. Of course, if we predict not spam and it's actually spam, it's a false negative. And that's annoying. So it's not, it's not so bad, but there's some cost associated to that, because now you have to filter through more emails yourself, right? So a decision theory framework would say, instead of just taking the most probable label, i.e., whichever instead of deciding what label to emit based on this, right? What we want to do is emit a label that minimizes the expected cost, okay? So that's the cost of predicting y hat I if it's really y twiddle I, okay? And this expectation is with respect to y twiddle I, the output of the model, okay? Sorry, yeah, is with respect to y twiddle I. So the point is, and we'll go through an example on the next slide, which I always butcher every single time I talk about it, even though it's very simple. So hopefully I don't butcher it as bad as I did in the last lecture. Even if spam has a higher probability, in other words, if this thing is actually higher than the other, right? Predicting spam might actually have a higher expected cost, which means that you should predict not spam instead. Okay, cool. So let's see if I can not butcher this next slide. It's just the calculation of this thing, but it's sort of annoying, right? So let's consider a test example. Okay, so we plug this in, and our estimate of y twiddle I, before we return anything, before we make any sort of decision, so on and so forth, our estimate that it is spam, the probability of that, we assign the value of 0.62. Okay, that's what our model does, right? Then under this table, right, we need to compute two things. We need to compute the expected cost of ultimately returning spam, averaged over y twiddle I, right? And we need to compute the expected cost of returning not spam, averaged over y twiddle I, okay? So our model is producing y twiddle I, right? Or would produce y twiddle I. So our model would produce y twiddle I equals spam with some probability, and it would produce not spam with some probability, 0.6 and 0.4, right? But the cost, right, of returning y hat I spam given that y total I is spam, and so on and so forth. Basically, looking up the cost of these two in this table, we compute the expected cost of returning spam, this label spam, as 40. So here we have y total I equals spam given x total I. This term right here is exactly what we have here. It's 0.6, right? So we know y total I not spam is this term, right? So we're just averaging over y total I, the potential outputs of our model, right? And the cost of actually returning to the user y hat I of spam, given that y total I is spam, well, that's okay, that's 0, right? The cost of returning y hat I is spam if y total I is not spam is here. Okay, that's 100. And when we compute the probability of that occurring, it would occur 4/10 of the time, right? So the cost of ultimately returning spam, given our probability estimate of spam, right, is 40. Okay, the cost of returning not spam at the end of the day under this decision theory framework averaged over our model prediction. So great. So y total I equals spam given xi. Well, we already know that's 0.6, right? And that's the cost of returning spam when y hat I is not spam, right? So that's 10. That's this guy here, and this last one comes from here. Okay, so the cost of returning not spam, given our estimate and this decision theoretic set of weights, is 6. So in this particular case, even though spam is more likely, right, because we have this decision theoretic framework where there are weights associated to each of these, if we try to minimize the cost, we should find the cost that's least that's smallest, that's this cost, and we should return not spam even though it is spam, because the probability that the message is spam is not high enough to be worth the risk, right? In other words, if this 0.6 turned into 0.9, for instance, this would be 0.9, this would be 0.1, this would be 0.9, this would be 0.1, right? This is no longer 40, it's 10. This is no longer 6, it's 9. Is that right?
Yeah. Yeah, that's good.
That's right, yeah. Okay, so I guess if there was, this is for 0.9, we'd still actually return not spam. But it's pretty clear that if we made this slightly slightly larger, is that right? Yeah, okay. So like if it's 99%, right? This is 0.01, 99, whatever, right? This will be 1. This is approximately 10, right? And we should return spam. But this basically says that only if our probability of spam under our model is very high, given these costs, should we return spam. Yeah. Great.
How do you determine which cost value to use?
Oh, okay, thank you, David. This is, and this is, I guess Jiu also asked this. This is largely a user preference, right? At the end of the day, the only way that you can actually set these values is, for me to tell you that I'm okay with having a certain amount of spam come through, and I really, really, really don't want to miss a message from my mom, right? So for our purposes, these will just be handed to you from the outside from some sort of user interface where the user expresses their preferences. There are other ways of estimating these sort of these costs for users. Inverse reinforcement learning is actually related to this. So if you're really interested, that's kind of a place to go look. Or preference learning is another name for it. How would you determine the values in more life or death situations? Well, yeah, I mean, this is that if you want to go through, like, you know, preference learning and decision theory is a big deal. It's but we're not going to talk very much about it in this course. Obviously, yeah, exactly, Declan and William are talking about, like, putting a value on life. Other applications of cost are likely to be very, very different, right? So false positives may be okay in cancer screening, like, but false negatives would be a really bad deal, right? You know, when you have cancer, but you are diagnosed as not having it, that would not be good, right? Yeah, you know, there's a fun article on, like, decision theory and darts, like, where should you aim on the board? Like, should you aim at 19 or 20, which is the one that gives you the highest expected score? That's important. And this decision theory framework can help with unbalanced class labels. Am I missing something here? Yeah, so Akeem asks another really good question, I think, right? Yeah, so here's where it gets a little complicated, right? So Akeem writes, so when we are actually training the model and trying to minimize the expectation of cost, we'd be tweaking the model to change the probability, or we're tweaking the actual decision. So it's complicated because such a model is over parameterized, right? So there's a probability estimate, and then there's a what value do we actually return. So for now, we're going to sort of try to keep them separated by saying the decision theoretic values are just going to come from user preferences, and they're going to be fixed. And we're going to estimate probabilities and then do something with them within the decision theoretic framework, right? If you try to optimize both through some sort of gradient descent procedure, you have to be very, very careful because the model is over parameterized, right? And that's this shows up all the time, right? The objective that you would be trying to maximize is not the user preference, because you don't actually know the user preference, right? There's no label of the user preference, right? They might give you a cost if you ask them to, but the only labels that you have are basically, is this spam or not spam, right? So you can really only train that classifier and then do something post hoc in the framework we're talking about. I warned you about basketball as well, right? So this decision theoretic framework, kind of like, what's the difference between probability and, like, the value of the decision, right? So let's just remember, this is a 3-point line, and this figure basically gives you the field goal percentage of shots taken in various regions of the floor. So these are relatively high probability shots. 40 to 45% of the shots in this area are made. Lots of them are made here. They're close to the basket. And generally speaking, it kind of falls off from there as you go farther away. Not surprisingly, it's more difficult to make a shot. But there's a different cost, right, or value between the shots that are made outside of the black line, the red line that I drew, and inside. Outside 3 points, inside 2 points. And this has actually sort of changed the game of basketball, because the decision-making process eventually took into account the expected value of the score, which is to say 3 points times the 35 or 40% probability of making it actually ends up being a more valuable shot to take than anywhere in here, basically, right? So the game of basketball, the game of basketball has evolved to be very much an inside-out game. Shots here, and nothing in between, because, like, shooting in between is a really bad decision. Okay. Questions? Oh, Christopher, maybe you go by Chris, I don't know. When we're using conditional probability estimates of like a trigram given spam for some spam filter like Gmail. Would you have to have a massive database of probabilities for words prevalence of spam? So you couldn't download the classifier offline because there are so many words with probabilities. I think the simplest answer is yes. So you have to think about what the model is that we're talking about here. And the model that we're talking about here is indeed a bunch of conditional probability estimates, right? So you need one of those for every possible feature value in or dimension in your feature vector. Now, is that really big or is that really small? It's kind of in the eye of the beholder, right? Like your client is almost certainly not going to run that, but there would be a web service or something like that would hold all those parameters. You can just pass a set of emails through that and assign a label as those emails stream through. So yeah. Cool, good. Any other questions here? Thank you. Excellent questions and comments so far, except for the unit of currency of pickled eggs, which seems to be sticking around for an unfortunate period of time in this course. Cool. Also, I just noticed, although it's in line with my taste in humor, I would like to point out that using Richard Stallman's name as your username for this could be considered offensive by some people in the course, and maybe perhaps you might want to think about not actually using that because we'd like this to be an inclusive and safe space, if that's okay. Anyway, moving on. So we've seen a couple of different classifiers. We're going to speed up just a little bit here in this course. We're about to see a third, right? But let's think about this. We've got decision trees and we've got naive Bayes. So let's compare them just a little bit. We know the decision tree program looks like this, and estimating or learning one of these programs means figuring out all of these parameters and doing it in our way, in a greedy way, but there's a combinatorial search problem that we have to think about and solve. Naive Bayes has a model structure that looks like a bunch of conditional probabilities that we need to estimate, right? And then we decide a class based on that. So decision tree is a sequence of rules based on one feature. Naive Bayes simultaneously combines all of the features, right? Decision trees, you have to pass over the data once per depth in the tree, or basically once per decision stump learning bit. In naive Bayes, you just run through the data one time to count everything you need. Decision trees, we like learn the model via some greedy splitting algorithm, right? It's an approximate, the approximation comes into the form of a greedy algorithm for estimating the model. In naive Bayes, we make an unrealistic but makes it useful conditional independence assumption. In decision trees, when we test, we just look at the features and the rules, right? So we don't have to look at the entire feature vector. In naive Bayes, when we test, or we make a prediction, a test prediction, we have to look at all the features. In decision trees, we already recognized, some of you did anyway, that when you get new data, you might actually have to change the entire tree. For instance, even the root decision stump might be different under our greedy procedure. In naive Bayes, you can just maintain this count of these probability estimates on some server, like Christopher pointed out. And you can just update the counts as you get more data, right? And decision trees are generally fairly accurate if simple rules based on individual features works, like symptoms of diseases or something like that. And naive Bayes works pretty well if the features are almost independent given the data. Like basically the bag of words assumption isn't crappy, right? So cool. All right, so we've got two pretty major, pretty powerful algorithms under our belt. Awesome, okay? How about number 3? And this one's maybe the easiest one in the entire course. And it's one that, because of its name, eventually you'll get confused about, but it's super simple. Like it doesn't get more simple than this, right? And it's pretty effective, and it allows us to think about some things. So we'll go through this really fast. K nearest neighbors. An old simple classifier is K nearest neighbors, KNN. dirt simple. To classify an example x twiddle I, you look in your training data and find the k training examples xi that are nearest to x twiddle I. Then you give the class label to x twiddle I according to whichever the most common label of the nearest training examples is. Okay, so here's our favorite allergy example. We have our feature matrix x, our output labels y, and we have a new test feature vector x twiddle I, and we want to assign it a label. So what do? We go into x and we say, for instance, compare it in some sense to all the feature vectors in the set of our training examples, and we find here the 3 nearest neighbors. The labels for those 3 nearest neighbors in this particular case are all ones. So the most common label is sick. Great. So we just say that is sick. Okay. Doesn't get any easier. Okay. What k-nearest neighbors does is give us an opportunity to think about feature spaces in it from some geometric perspective. So let's say we have 2 features, feature 1 and feature 2, and we're given labels of noughts and crosses, right? So since there are only 2 features, we can plot these as we've done before, right? So we've got feature 1 here and feature 2 on the vertical axis, and the data points are where they are, and the labels are noughts and crosses. So if you get new examples, test examples that you want to classify, those are going to be points in this feature space as well. And what you can do is just ask what their, in this case, 5 nearest neighbors are, and look at the labels on those neighbors and return the most common label in that set. So this example has labels, 0s and 1, 4 noughts, 1 cross, right? So we'll label that a nought. And this one has, all cross labels. So we can classify that as a cross, right? Cool. The assumption in k-nearest neighbors is some sort of smoothness in feature space, basically, right? Examples with similar features are likely to have similar labels. And this might seem like a strong assumption to you, but in fact, actually, basically all decent classifiers, all classifiers basically rely on this assumption. If this isn't true, then maybe there isn't actually anything you can learn, and you're in the no free lunch territory. And of course, different methods differ on how you define similarity. The most common distance function that we're going to use is Euclidean distance. This formalism over here should be familiar to everyone, basically. It's the length of a vector. This notation, which we'll talk about in much greater detail in the course, is going to be new to a number of you. That's the norm of a vector. And in particular, when we don't put a 2 here, the default is the 2 norm, and this is the 2 norm here. And let's just remember that if this vector is xi and this vector is xj, right? The difference is this vector, and what we're looking at is the distance of the length of this vector right here. So that's the distance between these 2 vectors, right? Okay, great. And clearly, in order to compute the Euclidean norm or the 2 norm, basically you need to compute something over all of the dimensions of the feature vector. So this runs over D, right? So it's an OD computation to calculate the distance between a pair of vectors, right? So we can think a little bit about k-nearest neighbors. It's worth doing. It's important. So what's the effect of k in k-nearest neighbors? Well, with large k is a hyperparameter that you might choose via cross-validation or something like that. A k-nearest neighbor model will be very simple, right? If you think about it, if you set k, the number of neighbors, equal to n, then all of the data are your neighbors, right? And if you take the mode of the labels as the thing that you return, then with k equals n, you just return the mode of the labels. Right? It's a very simple classifier. And very smooth because it returns the same value for the entire feature space. Basically, the model gets more complicated, and this means basically this expressive, the decision surface gets more wibbly wobbly, so on and so forth, right? The model gets more complicated as k decreases, right? So when you go from k equals 10 to k equals 3, right? For instance, what happens around here is rather different. Like if you put a test point in any of these particular spots, the 10 nearest neighbors give you a different answer than in the same part here where you just need 3 nearest neighbors, okay? So And in fact, you can go all the way down to k equals 1, which is just you look to find the nearest point and you would give it that label, right? So basically, the effect of k on the fundamental trade-off is that as k grows, this is a little bit of a misnomer here. So I'm just gonna, I know we were talking about training error increases and approximation error decreases because there's no training here. So don't worry about this very much. This is just like a, you'll understand it in just a second, right? It's sort of clear that as k grows, training error, whatever that is, think about this as leave one out, cross-validated training error or something, leave one out, cross-validated error, right? These guys are misclassified, right? Over here, these guys are not misclassified, right? Because one nearest neighbor, right? So as k grows, training error increases and the approximation error decreases, right? So fine. K nearest neighbors implementation, there is no training phase. What would the graph look like when k equals n? Sorry, there's no graph. It's just, what would this graph look like? It would just all be one color, 0 or 1, right? Red or blue here. That's what you mean, yeah. There is no training phase in k nearest neighbors, so-called lazy learning, my favorite kind, right? The model is the data, okay? That's weird, right? So this is obviously a different model class, and that's gonna come up in just a second, right? So you just store the training data, and if you just use a pointer to the data, then that's your training. You just set the pointer to your data and you're done, right? But predictions now are really, really expensive, right? Because basically you have to go through the entire data set all in every single time you want to classify a test example. And for every one of those points, you have to do an OD distance calculation for everyone. So the prediction time grows with the number of training examples. And there's ways to reduce this cost, space filling trees, KD trees, various hashing techniques, locality sensitive hashing, that sort of thing. There's a whole body of work on how to make this fast, but in principle, you basically have to do a comparison to everything, right? And storage is expensive, so you actually need to store all of your training data, all of your entire feature vector and your entire label vector, right? Feature matrix and label vector. So memory grows with the number of training examples. And in this course, the distinction between what we call the parametric model and a non-parametric model is exactly that. So this is also going to be a foreign notion to a number of you probably now, a majority of you, is the idea that there are parametric models and there are non-parametric models, okay? So parametric models are easy, right? Parametric models have a fixed number of parameters, right? In other words, the trained model size is constant as a function of the number of training examples, okay? So naive Bayes, one of the models we've looked at, just stores the counts for all the features, right? To compute the conditional probabilities. That's constant in n. The count vector doesn't grow in it, right? And a fixed depth decision tree also just stores rules for that depth, okay? Does constant in terms of n mean independent from n? I think I'm going to give the answer of yes to this here. I think that's the easiest. Wouldn't there be more words to store counts for if there's more data? And thank you for changing your username for everyone's benefit. I appreciate it. I assume you did. So yes, but if you remember, we said that we're going to use a fixed dictionary, right? So if you let the dictionary grow, then it becomes a non-parametric model. And if you, this is really subtle and this will blow most people's minds, but if you assume that you don't have infinite precision in your counts, then it also grows with the data, right? I will answer the question about the problem with Richard Stallman in just a little bit at the end, after the end of class. So anyway, the point is that in a parametric model, you can estimate the fixed parameters more accurately with more data, but eventually more data doesn't help the model. Is somehow too simple. Like it's not going to grow in complexity with the data. Now in parametric models, on the other hand, the number of parameters grows with n. The size of the model actually depends on n, right? So the model gets more complicated as you get more data. Another way of thinking about non-parametric models is that they actually have an infinite dimensional parameter space, but that is not the perspective we take here, even though they're basically equivalent. What we'll take in this course is that a KNN stores all of the data. So the model, the size of the model, in fact, actually, if you wrote the program, if you think about, we've been talking about supervised learning as program induction, like the program that you write or would return as a classifier is a program that has to contain within it all of the data, because you have to always be able to actually loop through the data itself, right? So the size of the model is OND, right? And another example of a non-parametric model would be a decision tree, for instance, a decision tree whose depth grows with the number of examples, right? So you say, like, I get more examples and I'm going to just grow the depth of the tree, right? Cool. The point of this is that the real point is that parametric models have bounded memory. So as the number of examples increases, the memory used by the model asymptotes. And that's this distinction that I wanted to, discuss it in terms of n mean independent from n, not strictly, right? So that it basically says that there's an asymptotic limit on the complexity of the model. It's limited as n goes to infinity. Non-parametric models are not, okay? So they will continue. Right? They can go, like the memory can go to infinity as n goes to infinity. So what does n look like in k nearest neighbors? Right, with small n, so we're gonna fix k and we're gonna choose the value of n. With a small n, k nearest neighbor model will just draw a hyperplane. Basically, it'll be very, very simple, right? But as n increases, even as k remains fixed, the model gets more complicated, i.e. this decision surface gets more jaggedy and more specific to the problem, right? So it gets more complicated, which means it requires more memory, but it also is able to detect subtle differences between examples. And we're not going to go into this. This is one of these tan slides, but k-nearest neighbors have very appealing consistency properties, right? As n goes to infinity, the k-nearest neighbor's test error is less than twice in the best possible error under some assumptions, right? And there's a very nice theorem called Stone's theorem. You can look it up if you wish, that the k-nearest neighbor is universally consistent, which is to say that if k over n goes to 0 and k goes to infinity, then a k-nearest neighbor converges to the best possible error. So in other words, you can actually choose k to be like log n, and this holds, right? And this is, the k-nearest neighbors is the first algorithm to be shown to have this property. Now you can ask,
KNN unsupervised learning?
No, that's a good question, Shaunak. K-nearest neighbors is definitely supervised because you have the label for each example and you use the labels of the training examples to predict the label of the test examples. And those labels have to come from some external supervision source. Okay. So Stone's theorem about k-nearest neighbors violate the no free lunch theorem, i.e. is this k-nearest neighbors the best model ever? No, because it requires a continuity assumption on the labels, and that may not actually be true, right? And consistency says nothing about the non-asymptotic regime in which we always operate. It doesn't say anything about finite n, okay? So it should be noted, though, that with parametric models, there's almost always an accuracy limit. So even with infinite n, you might not be able to achieve the optimal error, whatever that is, for the problem that you're looking at. Whereas many, if not all, non-parametric models like k and nearest neighbors converge to the optimal error. So this is the number of examples n, this is the test error. The parametric model will asymptote because of the fact that it has finite capacity. Non-parametric models can push this gap to 0 in the in limit. It's also worth pointing out the cursive dimensionality, right? So, and this is a problem that this is a phrase that we'll use, and its meaning is probably clearest and easiest to establish in your mind right now, which is that if we're going to do k-nearest neighbors, which is kind of at the core of every machine learning method, the volume of the space that we need to compute these distances in grows exponentially with dimension. So like if you think about like a circle that has an area of r squared, and a sphere has generalized area of r cubed, and hypersphere has generalized area of O to the 4, so on and so forth, r to the 4. The point is that in order to fill or have a nearby point in this high dimensional space, or in the the same subvolume of this high dimensional space, you need an exponentially growing number of points, right? So nearest neighbors might be really far, even with a large n. So k-nearest neighbors is also problematic if features have very different length scales, so that you can normalize the length scales of features before you put them into a k-nearest neighbors algorithm. However, k-nearest neighbors is very good usually and pretty hard to beat. So before we get to questions, let me summarize. Decision theory basically says you have some sort of predictor, some sort of classifier, something like that, but there are costs associated with making certain decisions. So perhaps when you return the result, you should actually take those costs into account by computing expectations over various quantities in order to predict the costs of the prediction you make. K-nearest neighbors, we just went through, basically looks for neighbors in some high dimensional feature space, and then gives you back the label that's most frequent amongst its neighbors. It usually works pretty well. We talked about non-parametric models, right? And how their complexity or expressivity grows with the number of training examples. They have appealing consistency properties. However, in all of these cases, when the feature space grows in dimensionality, nearness for this sort of thing can be difficult it can be difficult to fill up space enough to solve the coupon collecting problem that we talked about before, something like that, because of the cursive dimensionality, i.e. distances grow as the dimension of the feature space grows. That's it. Cool. Great. Questions? Stick around for a while. How many people stuck around? 70. Oh, that's pretty good. Okay. Okay. From William, can't you use feature scaling? Yes, you can, and you probably should if you're going to use a k-nearest neighbor implementation out of the box, right? It may be good, it might not be good, but generally speaking, you probably want to normalize the units of or descale your units by z-scoring them or something like that. Can you use k-nearest from Ramon? Can you use k-nearest neighbors to make more data to train another algorithm, a parametric one? A k-nearest neighbors is not a generative model, so it can't be used to make more data. It can be used to assign labels to unlabeled data, but then you don't know whether or not it's right. So it's a good thing to think about, Ramon, but I think you're not quite on the right track here. So no. What does features having different scales mean? Can you normalize that? Let's think of the allergy example, right? What units would you use for the features in that, right? Like you would have some number of cups of milk. You would have a unit number of eggs that you eat usually, right? 1, 2, 3, 4. You might have grams of broccoli and kilograms of sugar, and who knows, right? So these units are actually going to be all over the place. That means that the numeric values are different, which means that when you're computing distances, like distances in one feature dimension, the numbers will correspond to different semantic meanings, right? So like if you want distances to be equal amongst feature dimensions, then you probably need to remove the unit. Great. What about k-nearest neighbors for from Mr. Big Toe, what would be the cost of pre-computing the decision boundary for k-nearest neighbors? This is a really kind of surprisingly insightful question in so much as it's kind of wrong-headed, and I don't mean that in an offensive way, but the point is that you can't represent the decision boundary of a k-nearest neighbor without actually using the data. The data is the data is the form of the boundary, right? So there is no notion of pre-computing the decision boundary because the data defines the decision boundary, right? Yeah, that's a tough one. What about from Hakeem? What about k-nearest neighbors for categorical data? I0, 1, no problem at all, right? If you give me, that's from the very, very beginning, we said, okay, we're going to turn everything into numerical feature vectors, and we're going to compute distances between those, and whether those distances make sense or not is, who knows, right? So you could imagine there were different distances we talked about, like there's the, what's the distance between sets? So we had like Hamming distance, we had, why do I never remember the one between sets? We had edit distance, we have intersection over union, whatever, I get it. Jacquard, thank you very much, Alan, thank you, yeah. So like the distances that we use for k-nearest neighbors can be problem specific. We just talked about Euclidean distance here, but you could use an L1 norm, you can use different distance metrics, so on and so forth. Siddharth, I hope everyone feels the way that you feel. Thank you for your positive commentary. It makes me feel good. Could we make a probabilistic, from Alan, could we make a probabilistic k-nearest neighbors where added samples will have attached the probability of being the assigned label and weighted as such? Okay, just wait until we get to Gaussian mixture models, hold on to that. Or mixture models in general, or k-means, which people almost always mix up with k-nearest neighbors because they're really close. One is an unsupervised method and one is a supervised method, and you can mix and match between them, but I don't want to totally mess everybody up who's listening. So for now, punt on that, Alan. Oh, Siddharth, I fully intend to make this class as miserable as possible by the end. Thank you, though. Daisy, yes, we could be literally comparing apples to oranges, indeed. Although the units of those might actually be the same. So depends. As K prime grows from Lex, why does approximation error decrease? That's a good one. We'll have to flip back for that. Jacquard, good one. Find the name to have to iterate over all in. Lex, yes, you have to iterate over all in. Okay. All right, Lex asked a tough one. Okay. Nope. Where is it? Let me just answer.
521.
Thank you. The easier way to think about this is that when you're in this regime, down here, in this regime, oh dear, never mind. When you're in this regime, the chances of overfitting, in other words, the chances of the shape of the decision surface being too specific to the training data is very high. right? So it's easier to think in this direction, right? So as you go this way, the shape of the decision surface is necessarily going to be smoother. And when you have a decision surface that's smoother, almost always that will generalize better because it's not so specifically tied to the exact training data set that you have, right? So that's why approximation error decreases as you increase K, because the wiggliness, the specificity of the decision surface goes down, basically. Okay. And to, so if there are no other questions, we should leave because it's past the time for everyone. But let me see how many people are on. I don't know if the Stallman people are on, but people should look up Richard Stallman, the founder of the Free Software Foundation, something like that, and was released from his position at MIT for consistent a consistent pattern of harassment, in particular gender-based harassment. So I don't think we need to be having that represented in the class in any way, shape, or form, basically. Any other questions? Comments? Beautiful. Yeah, no, yeah, I'm certainly not a snowflake, and I don't expect many people in the class. Many people in the class are snowflakes, and whatever. Everybody has their own deal. But let's be careful not to even unintentionally offend. Yeah. Cool.
Thank you.
See you Wednesday.